My name is Bill Johnson. I'm a professor at the University of Utah in Salt Lake City, Utah. I want to show you today a technique, software that's available for people to use for various purposes related to colloidal transport. We call it Parti-Suite. It has 3 modules that I'll briefly explain here. The objective of this video is to explain the torque balance, or at least demonstrate it. It's explained in all the related publications, and to show one application of that. So this page here is my webpage at wpjohnsongroup@utah.edu. Excuse me, wpjohnsongroup.utah.edu. And under this main page is Parti-Suite software, and that page looks like this. It's particle trajectory, surface interaction, and upscaling software described in our publications that I'll talk about in just a bit. But these are Fortran and MATLAB executables. The MATLAB are the most user-friendly. They come with graphical user interfaces ported from the Fortran by Eddie Pazmiño, with significant help from me and my student Cesar Ron, but Eddie's the one who led the porting to MATLAB and the development of these GUIs with our input. So he's done an excellent job here. And I would suggest people start with these. And our goal is to basically collaborate with people to provide a platform that people can build on. Because there's a good 20 years of knowledge incorporated into these to this source code, and I want to share the source code. It's just that I want to have a user base before we distribute the source code, so that it just doesn't get snapped up by some commercial entity that might want to market it. And so we want to provide this free. Once I learn how to manipulate this on GitHub, that would probably be the working space for this. So here's the example. Well, here's a little bit more description of the software and then the example. But what the software does is it takes the nanoscale interactions through the DLVO, extended DLVO theory shown on the left here. The upper panel is classic DLVO theory with in this case, the electric double layer in red, the steric in pink, and the steric in gold, and the Bourne forces in magenta, I guess, and I should have mentioned first, the Lewis acid base in the green, and the van der Waals in the blue. And so these, of course, depend on the fundamental parameters for the surface, for the system you're looking at. Often people are looking at polystyrene, water, glass, but all the components, all the parameters are there for you to look at other fluids, to look at other surfaces. Now, what's on top of this is that we can include heterogeneity of given size and show the effect of whether that heterogeneity fills the zone of interaction between the colloid and the surface. So we look at whether it fills 20, 40, 60, 80% versus 0 is mean field. And you can see that as the heterodomain, which we take as oppositely charged to the bulk surface, as it fills greater fractions of the zone of interaction, it eliminates the barrier. And these are also plotted in terms of not just force, but also energy in KT in the simulations, in the output from the simulations. So the point is, it takes those nanoscale interactions, it incorporates them into a full force and torque balance done in a Happel cell, although we have other geometries too, but I'm showing the Happel here, and it's the one that's been best developed for the graphical user interface. So you get these trajectories. This plot shows the trajectories with color according to separation distance from the collector surface. From those trajectories, again with a full force and torque balance described in the publications. Let me just stop for a second. So with those trajectories, the model obtains, in the upscaling mode, the residence time distributions of colloids before attachment on the collector. under favorable versus unfavorable conditions, and also outcomes. Where do the colloids end up? Do they exit? Do they attach? Do they accumulate in the beer flow stagnation zone? Those kinds of attributes. And from those residence times and from those outcomes, the continuum scale rate coefficients are derived so that the breakthrough elution curves can be developed, as shown here, for a 3-pore volume injection, and then slow elution with extended tailing predicted by the slow-moving colloids near the collector surfaces, and then the profile of retained cells, whether they are immobilized, attached, or moving in the near surface slowly along collector grains. Now, there's assumptions built in this. These are described in the publications. The dashboard, I'll get to those publications in a second. The dashboard for the DLVO, extended DLVO module, is fairly complex, but very useful because it allows you to change the fundamental parameters of the fluid, the surfaces, and so on. And not only does it allow you to do that, but it allows you to change the system. So if you have, excuse me, and most people do, the extended DLVO parameters for each of the surfaces, whether it's polystyrene and glass, you can change the system to instead be polystyrene water glass, could be polystyrene water polystyrene. If you're looking, for example, at accumulation of colloids onto colloids on surfaces, so that you can then look at the DLVO interactions between the colloids. Furthermore, it provides the ability to calculate these things from the fundamentals. This isn't a live screen right now. I'll show you that in the model in just a minute. But not only does it allow you to calculate these from the fundamentals, but it allows you to work with coded systems. And it does this not only for the van der Waals forces, but for the acid-base forces, for the work of adhesion, which is really critical to the torque balance for detachment, and the contact radius that results from deformation of the colloid. You can calculate that from fundamentals. So it gives you a great deal of flexibility. And then again, you can toggle between looking at the mean field surface versus over header domains, and you specify the header domain zeta potential, and the zone of interaction between the colloid and the surface is calculated based on the fundamentals. So these things are available in the XDLVO module of Parti-Suite. And then the Happel sphere colloid trajectory simulations are shown here, this dashboard. And you can see it's quite complex, but the point is that you can get these interaction parameters from the XDLVO module and populate them here in the trajectory simulations in order to conduct these simulations for complex systems. What else do I want to say about this here? I'm going to show it in operation here in a bit, so I don't think I need to say too much more here. It's just got a lot of flexibility for running loading simulations, or once you run a loading simulation, you can perturb the system to see whether you can force detachment, and that's in perturbation mode. That is enough for now. So when these models are running, specifically the trajectory model, it shows you a control panel, not a control panel, it's a panel of results. So you can see the separation distance between the colloid and the surface across time. Whoops. You can see the drag force acting on the colloid in the normal direction or in the tangential direction across time. You have a two-dimensional from the side view of the collector, so the colloid enters from the top, depending on your injection radius that you choose, and you can watch its progress through the bulk fluid. This is the bulk transport model with all of this information, and additional 4 panels on the bottom give you the colloid velocity in the normal, colloid velocity in the tangential, and I forgot what this one is. I got to think about that. And then the colloidal force in the normal. And so the bulk transport window has all this. Then when the colloid moves to within the distance over which van der Waals forces extend, it gives you the near surface transport when the van der Waals starts to become significant. And what happens there is that, I'm going straight to the bottom right panel, the attractive and repulsive forces coming from van der Waals attraction and electric double layer repulsion, and the extended forces those will balance because the colloid is sitting in the secondary minimum. And so you can watch in the Z versus RXY dimension, that is the side view of the collector, the colloid moving along the surface of the collector, and all these other panels are self-explanatory. You can see the separation distance here in this panel, static panel, is 20, 30, 40, about 40 nanometers from the surface, typical secondary minimum distance. Okay, so those are what you get when you're running the model. At the end of the run, you get panels showing you what happened. Okay, so that this is the separation distance as a function of Z coordinate. Z coordinate is from positive radius of the Happel collector, which is the grain plus the fluid envelope, down to negative Happel radius. And so starting at the positive Happel radius, the colloid has a separation distance far above the surface, moving towards the surface, and then attaches in these cases because there is heterogeneity that can arrest the colloid. Now this is a zoom in of that H versus Z so that you can see the colloid get to the secondary minimum and then find a heterodomain and attach. In the two-dimensional looking down on the equator of the collector, you can see the attachment points of the colloid. If it had exited, it wouldn't be blue, it would be red. And then the trajectory is shown in 3 dimensions with the separation distance corresponding to color. So red is large separation distances going down to blue is attached. And in between is the near surface environment. Okay, so those are the things that the model gives you in the GUI. The guts of the model are described in these publications and preceding publications. This work is cumulative, going a long ways back to the 2000s, early 2000s. Pardon my voice. And so these involve authors like, in preceding publications, Xiqing Li, Eddie Pazmiño, Jake Troust, but they've culminated in these publications here with Anna Rasmussen, that exploring the impact of roughness and how to parameterize that. Cesar Ron, exploring the heterogeneity and what the simulations suggest, how they constrain the size of the heterogeneity and spatial densities of it. Kurt Van Ness constraining the force and torque balance at the surface. All of these compare experiments to simulations to constrain the parameterization. And then this one in 2018 by me, led by me, there by everybody, of course, exploring upscaling of the pore scale trajectory information. And those are provided, the specific references are provided on my website. So the idea here is to explore in this video the detachment of colloids from either the collector surface or from accumulated colloids associated with the collector surface, attached to the collector surface. And so I want to jump right to the latter. What can you do in order to simulate agglomerated colloids on a collector surface and detachment of bunches of those colloids as that deposit builds out into higher fluid velocities towards the center of a pore? And so I'm no artist, so what I did is I'm showing you the schematic from Kurt Van Ness's paper, and the point is he did experiments looking at deposition on a surface and understanding how the fluid shear impacted that deposition. And I want to point out here that I'm seeing articles that are characterizing this kind of detachment as a balance between hydrodynamic drag, which operates tangentially across the colloid, versus an arresting, versus a normal force is what I'm seeing in these publications from DLVO operating normal between the colloid and the collector. And of course, comparing those directly doesn't really work because they're not even oriented in the same direction. And so what needs to happen, in fact, is that the analysis needs to involve a torque balance because it's rolling that initiates detachment, as well established in the literature, and including classic literature. And so the torque balance is schematicized here. The torque balance originates, of course, from fluid drag, fluid shear,
but it's operating with a lever arm that corresponds to deformation of the colloid on the surface as dictated by the rheological properties of the colloid. And so you have an arresting torque that is the normal force attracting the colloid to the surface, coupled to this lever arm that is the contact radius in the contact area of the colloid and the surface. And then you have a mobilizing torque that is the fluid drag, fluid shear, operating on a lever arm defined from this axis of rotation, okay, which is the edge of the deformation field on the colloid. And so that torque balance has been incorporated, tested, first of all, in Van Ness et al., but then incorporated into the simulations. And the rheologic properties of the colloids can all be specified there. The default values are for polystyrene, latex microspheres, interacting with glass. But again, you can recalculate those parameters using the fundamentals panels on that DLVO module. And then in the trajectory simulations, you can play with detachment. You can do it for single colloids, or as I'm schematicizing here by ripping off some net clip art on the web. You can think of these as great bunches, collections of colloids interacting with one another. And the point is that you can define, first of all, you can create these in the trajectory simulations, at least spherical versions of these, by taking a certain radius of colloid. We'll call this bunch a colloid, but it's got roughness, okay? And so we can take, say, a 10 micron colloid and put 1 micron roughness on it. And therefore, call the collector a polystyrene great bunch of a certain radius with 10 micron roughness, 1 micron roughness. And the colloid is a 10 micron bunch with 1 micron roughness. And we can simulate that in that system to look at the fluid velocities that can force detachment of those representations. And so I'm going to lead you through now in the model these aspects, the XDLVO parameters, where you can change the fluid properties, the van der Waals interaction and UDL interactions from the fundamentals, the work of adhesion and contact radius also from the fundamentals, and then you can input those into the trajectory model to look at the velocities that allow attachment and detachment, okay? So in doing that, one has to keep in mind that you're setting the time step parameters, so you're going to get junk if your time steps are too high. Your injection radius allows you to control how close to the axis you're injecting the colloid, in other words, to force it to go near the surface. If you're trying to quantify eta, well, you have to be careful about that, and I'll have a different video about quantifying eta. And then you control the header domain size that may or may not allow the colloid to attach to the surface, because remember that when the colloids approach the surface, there may be a significant barrier to attachment under unfavorable conditions, and you have to create landing pads, these header domains. And they have to be big enough not only for the colloid to find that landing pad, but to stick the landing, so to speak. And so the torque balance determines whether or not that colloid occupies a large enough fraction of the zone of interaction to allow immobilization. Okay, so I'm going to pause this. So when you go to open the software, remember that you have to right click and run as an administrator. So I'm going to open up the XDLVO software and show you some things about that. So hit yes for running as administrator. It takes a couple minutes to open up. It's not that heavy software, but it just takes a bit of time. So here's the XDLVO control panel. And as I said before, you can calculate things from fundamentals. So there's a bunch of default parameters just to guide people. This is for the polystyrene water glass system, but you can change all this. So if you want to calculate the van der Waals constant from the fundamentals, you can simply input your own colloid, collector, and fluid properties, and those are the dielectric constants and the refractive indices that govern the dispersion forces, London dispersion forces for the van der Waals interactions. It'll calculate that Hammacher constant that you can then put into the combined high micro constant that you can then put into the trajectory model. Okay, likewise, and I should mention why I'm on this, we also have coded systems for the van der Waals interactions, so that if you have a layered system, like a layer of, for instance, we've done experiments with gold-coated hollow glass microspheres. Using X-ray microthermography, you could specify the thickness of the gold layer and of the glass layer and have a layered system with both of those. I won't go into that. That's going to be another video, but the point is it exists. If you want to calculate the Lewis acid-base energies from fundamentals, you can put in the electron donor, electron acceptor properties for the colloid collector and the fluid. If you want to calculate the work of adhesion, you can put in the free energies of the colloid collector and the fluid and determine the acid-base energy at minimum separation distance and then the work of adhesion. Likewise, the contact radius is calculated here using the colloid Young's modulus and the Poisson's ratio, and you get to the combined elastic modulus and then get the contact radius. And so some of that is built into the particle trajectory. Some of this you can export from here. And so those things are all available to you. And the whole idea here, of course, is to facilitate your calculating these and innovating on the polystyrene water glass system. As I said, you can do that you can change your system from polystyrene water glass in this system to polystyrene water polystyrene, or polystyrene some other fluid polystyrene, by changing all these parameters. As I mentioned before, you can calculate the profiles for over the mean surface or over the header domain. You simply do that, calculate, and it shows that push calculate button, and it will calculate for you the DLVO profiles for the mean field, that is no header domain, or 20, 40, 80, 100%, 20, 40, 60, 80% coverage of the ZOI by header domain. All right, so that's enough of that. I'm going to close these profiles. Okay, so with respect to the trajectory simulations then, we can go to that control panel, and I'll maximize this so you can see it a little bit. The point is you can specify the number of colloids. Because this is configured in MATLAB right now for single core, you can run, depending on the conditions, multiple tens, maybe 100 colloids. That's not enough under unfavorable conditions to really quantify eta. So we parallelize this for really quantitative calculations of eta and the outcomes that lead to upscaling. Fortunately, we can parallelize MATLAB, and when people are interested, we can work with them to do that. But for now, this is really instructive in the single core mode. And lots of parameters here. Some of them come from playing with the XDLVO module. But what I'll focus on is if we want to represent a colloid great bunch, and I'm just going to do this for the polystyrene water glass system for now. But as I said, you can change it to polystyrene water polystyrene or polystyrene glycerol polystyrene, whatever you want. We're going to make a 10 micron colloid, and to make it a great bunch, we're going to take the asperity height on the colloid and make it 1 micron. So I'm going to make it 10 to the minus 7th meters to make it 1 micron. And so I'm just using the default fluid velocity here, and it's a little high because its default is made to run fast so that people can see it. So I'm going to lock it down an order of magnitude 1.6 times 10 to the minus 5th meters per second. I'm just going to run 2 colloids so it doesn't take too long. Obviously, you want to run this under contact mode, not perfect sync. Perfect sync gives you a reasonable approximation if you're not trying to look specifically at the torque balance. We got header. Since we have such a large colloid, I'm going to change the header domain radius to something more like, well, I'll leave it at this. Maybe this will show something. And go with all the default parameters for DLVO. the bulk multipliers, these are time steps are relative to the momentum relaxation time of the colloid, which is a good way to scale this. And so I'm going to knock this down so it's not numerically jumping too fast across the space. And I can talk more about these, but just for the sake of efficiency, I'm just going to show you right now. You can learn more about it in our publications too, how the time step is scaled to the momentum relaxation time. So I'm going to run this loading simulation for a 10 micron colloid interacting with a much larger glass collector. And what's the collector radius here? Grain radius is 255 microns. It's glass, so it doesn't really represent fully what you might want to play with here, but gives you the idea. And it's got roughness of 1 micron, so it's a great bunch interacting with a glass bead. So you see the control panels here as I described before. It's in the bulk fluid right now. It moved into the near surface. It's now moving along the near surface. I'll see if I can maximize this so you can see it better in the two-dimensional. It's moving along the near surface here. It is moving very fast in the near surface. And what's happening here, and now it's gone back to the bulk and just exited, okay? What's happening here is it's not finding a landing strip because these heterodomains are too small to bring the colloid in near the surface. And so I think we're going to see this happen for all of these, both of these colloids that we're simulating here. And I suspect if we simulated more, we'd see the same thing. That they move into the near surface, they skim along the secondary minimum outboard of the surface, and then find their way back into the bulk surface. And so this is shown in this H versus Z plot here, where they come down to about, it looks like to be, so 0.5 times 10 to the minus 7th is 50. So around 25, 30 nanometers. So they're getting close to the surface because they're so big, the van der Waals, the secondary minimum is deep. And they're getting within about 25 nanometers of the surface, but they're not getting to where surface friction kicks in. So, so the heterodomain's too small. So let's make the heterodomain bigger. Now, you can avoid this complexity, by the way, by just running it under favorable conditions and looking strictly at the torque balance under favorable conditions. We're going to create locally favorable conditions by increasing the heterodomain size. Let's make it, I don't know, 600. I mean, that's ridiculously big, but that's another conversation. So we're going to run that now with big enough heterodomains to arrest these colloids, practically favorable conditions around these heterodomains. And so the colloid's coming in from the bulk fluid into the near surface fluid, and now it should come into contact with the surface. And the question is whether or not it can immobilize, whether it can stick the landing on the landing strip. It's not in contact, so maybe that's not even big enough to allow these guys to attach. I may have to go into favorable mode so I'm not thinking around inside the heterogeneity right now. Because I have a high enough surface coverage, it should be able to find these heterodomains. Oh, this one's in contact, so there's stochastic showing there. It's all a matter of diffusion, creating some randomness here. It's in contact now, and the question is whether it immobilizes or whether it just keeps moving along the surface. And so what you see here is time is on the x-axis, and we're taking extremely small time steps. 1/100th of the momentum relaxation time. That might be too small. Maybe we should have made that 1/10th of the momentum relaxation time. We're accumulating traces, and what's happening is the colloidal force is increasing over time. You can hardly tell which direction it's running, but I know it's running this way. The adhesion repulsive forces in blue and red are also increasing over time. The area of the zone of interaction with heterodomains has gone to 1. In other words, it is over a heterodomain, slowly rolling, and it is not arresting. If it arrested, this would stop. It would show us a plot. And so that indicates this fluid velocity is too high for this size of colloid to allow its arrest. It is rolling along the surface on its little bumps. And so this would mean that it wouldn't arrest and would be almost equivalent, and I say almost equivalent, to showing that this fluid velocity is too high. It would cause erosion of these colloid bunches on the grain surface. Now, on the glass surface. Now, if you want to look at this for, a grape bunch interacting with a grape bunch in terms of polystyrene particles, you'd have to change the collector to have the characteristics of the polystyrene, but that's not difficult to do, as I showed you. Okay, so you get the idea here, and it looks like it's just going to keep rolling into perpetuity because, of course, nothing necessarily would change under these parameters. And so it's just going to roll along this heterodomain. Now, one thing we should do is have the side view plot of the collector so you can see how far along it's moving across the collector. But you can see these are very small, fractions of a second, so it wouldn't have gotten far. It is just slowly moving across this surface. I would have to abort this, and maybe I will. I'll pause this, and if it'll let me. Okay, I'm going to have to close CalTour to wake it back up. And the model's working hard right now, so it may... Okay, so now what we're going to try to do, what we'll try to do here is to reduce the fluid velocity by an order of magnitude to see if we then allow immobilization of the colloids. And obviously, factor of 10 is a big jump, but I'm just demonstrating this. You can narrow this by running additional simulations. So we still have a 10 micron grape bunch with 1 micron roughness, and all the same parameters we had before, and I have the time steps as we had before as well. So I run that loading simulation, and we'll see whether or not they immobilize. And I'm just running 2 colloids here, for example. So they're in the bulk, or it's in the bulk fluid. It's now moved into the near surface fluid. Oh, I forgot to set the larger heterodomain, so it's going to actually not get to the in contact. So we'll let these 2 run, and well, I'll stop this and I'll start it again when it's ready. Well, I am going to show this a little bit because this is the second colloid, and what's interesting about this, having reduced the fluid velocity by a factor of 10, is that they take a longer time now to traverse the grain radius or the grain circumference in the near surface and the bulk. And so right now I'll maximize this. This is in the near surface now, the second colloid. Moving slowly along the surface, its separation distance from the surface is consistently around 25 nanometers. So a deep secondary minimum. Here you can see on the right bottom panel the attractive and repulsive forces. They're in the 10 to the minus 12th range. You can see the colloid is moving, so piconewtons, and it's moving along the surface here because of fluid drag. It's not immobilized because surface friction doesn't reach out this far. And it exited because it's heavy, it came out. And so it's back in the bulk solution and it exited. So you see these trajectories of these 2 colloids. They never get within contact of the surface. Okay, so now what I'll do is run this again with a large heterodomain, like we did before, 6 times 10 to the 7th minus 7th. So that's 600 nanometer radius heterodomain. Again, I can explain more what that really represents. We don't have heterogeneity on the colloid, which makes for these large colloids necessary to have ridiculously large heterodomains on the collector. But this will be a reasonable demonstration, even though we won't need large heterodomains on the collector if we have heterogeneity on the colloid, which we're incorporating. Okay, so I'm going to run that simulation. The only difference between this and the one where they didn't immobilize in contact is that the fluid velocity is now 10 times smaller. And so we're going to check and see that once it comes into contact, will it immobilize? So it's in the near surface now, which means it's associated with the surface but not immobilized. And it will find, if the heterodomain is large enough to bring it into contact, when it gets over a heterodomain, it will then have the torque balance in contact. And I should say that The repulsive and attractive forces aren't balanced yet, but they'll move into being balanced. The time steps are very small in the near surface, and so, but eventually they will overlap. Okay, now I should have found a heterodomain by now, so I'm not sure what's going on here. Okay, I'm going to pause this and figure out why. Okay, so the 600 nanometer radius heterodomain wasn't big enough in this case, so I've now made it a 900 nanometer radius. Going to run that simulation and see, once it comes into contact, whether or not the fluid velocity that's now an order of magnitude lower than the previous simulation where we ran it into contact, see whether or not it actually is sufficient to rest it, immobilize it. So you can see it's in near surface now. It should soon come into contact and either immobilize or continue rolling in contact. Okay. That was very quick, even with the very small time steps in contact, but what happened there is that it came into contact with the surface and immobilized immediately. And so what you can do with this, of course, is we've learned that the order of magnitude lower fluid velocity allowed immobilization, so we've bracketed immobilization versus not immobilization. And one can play with the fluid velocity to understand what's that threshold that allows immobilization. And so if I go to the figure here, the magenta circles means that the colloid ostensibly immobilized, stopped rolling, because the you don't want to sit there and watch it roll forever, but we have a displacement factor that you can read up in the manual that allows us to terminate the simulation if it's rolling so slow that it's within some factor of diffusion, in this case 10% of diffusion. We have that true also in the near surface for colloids that get around to the rear flow stagnation zone and just bobble around back there. But this one, it was rolling so slow, it was only 10% of what it would move according to diffusion, which is obviously very slow, and so we called that immobilized. You have control over that as well, that factor. And then what that looks like in the three-dimensional plot, they didn't get very far. They got to near contact and stopped. They got to near the axis, sorry, in contact and stopped. So this is, I think enough to show you the capability to look at torque balances. One thing I didn't do here is look at those that were in contact